Welcome to part two of chapter one, just the general information about chemistry. We finished off the notes. We were talking about classifying matter and the different things that we have in chemistry. We talked about elements, compounds, which are pure substances, and we also talked about mixtures. And mixtures can be well mixed, which is a solution, or not so much. Just to reiterate, here's a compound. A compound and an element are pure substance. The difference between them is you can break a compound down into elements, but you can't break an element down anymore. Okay, so just kind of a review from what we talked about in the last part. Okay, when you have a mixture, now remember a mixture has variable composition. You can tell kind of because you can separate it. There's several different ways you can separate it. One of them is called distillation. What it does is it uses different boiling points. Here you have a solution and you boil it, and at certain temperatures, it it changes back from a gas to liquid, condensation. So then it collects it. Here's your condenser that does that. If you really want to see a huge distillation, if you go by in Mandan, they have the gasification plant and they have those huge towers. That's what they're doing. When you get crude oil has kerosene, diesel fuel, regular gas that we would call octane, has all kinds of things mixed in it. So they have to separate it. And so they use these huge towers. They boil it off and get your different colors. So that's how they do that. So distillation is a one way of separating mixtures. Another one is filtration. You guys may have done this before. You just fold a filter paper, put it into a funnel. And the reason why they have this stirring rod is when you pour it, it doesn't splash. Okay. But again, what's going to happen down here, what you have down here is called a filtrate. And then you're going to, on the paper, you're going to have your solid solution. There's also something called chromatography. In this case, what they did was they put ink and then you put it in a solvent, and the solvent can be water, it can be an alcohol, ethanol type solution. It depends on what you're trying to separate. And what will happen as the paper, you don't put right here, I wouldn't want the ink to be in the water because that'll mess it up. But you want to put it close to, and then what happens, just by absorbing it up, what will happen is you can see it separates into all the different pigments. So black ink has purple and blue and yellow and all these others. They actually use this to separate like pigments in plants, in paints, all kinds of things. So this is another way of separating. And again, these are just mixtures. Okay. All right. So when you're a chemist and you take measurements, we use a system. We use what they call the System International. Okay. It's the metric system. You can see we use kilograms, meters, seconds. Kelvin is an absolute scale for temperature, moles, that kind of stuff. We do not use the English system. We do not use inches and feet and pounds. We don't use that because they're not very uniform. When you think about it, we got 12 inches in a foot. There's 3 feet in a yard. There's 5,280 feet in a mile. It's not very uniform. The metric system is awesome because it's just tens, hundreds of thousands. All you do is move the decimal over. So it's really easy to work with. And the other thing is, everywhere in the world uses the metric system except for the United States. Even English don't use the English system, but we do. So if you were a well-renowned scientist and you did a paper and you recorded your results in the English system, most of the world would not understand what you're talking about. So we use the metric system whenever we take any measurements in science. We use the metric system. Okay, and again, there's a different base. Like if we're talking about mass, we're going to use grams, centigrams, milligrams, kilograms. If we're going to use volume, we use liters, milliliters, and so on. So there's a different base for each quantity. Okay, here's here's the standard rate between here, but you can see giga, mega, kilo, deci. These are just units. And again, they're all units of 10. So it's really nice. It's really easy to convert when you use the metric system. Okay, one of the most commonly used, or what they call derived unit, is volume. Okay, for us, like mass is very simply put on the scale. Well, volume, if it's a liquid, is really easy. You put it in a graduated cylinder and you just read it, how many milliliters. The problem with that is not everything is a liquid. Here in this case, these are regular shaped solid. And if you have a regular shaped solid, all you have to do is measure the length times the width times the height, and that will give you the volume. So they call it centimeter cubed. The nice thing about it is a centimeter cubed and a milliliter are the same thing. So that works out slick. But it's the number of units, and again, volume is a derived unit. It's how much space something occupies. Okay, and here they talk about a liter is a decimeter. A decimeter is one less than a centimeter. So if there's 100 decimeters, there's 1,000 centimeters, or if there's 10 decimeters, there's 100 centimeters. They move along that way, okay? But a milliliter, if you have a cube that's 1 centimeter by 1 centimeter by 1 centimeter, it would be 1 milliliter. Okay, here's how most of the time we measure volume. The graduated cylinder. And in the lab we have, this is 100 milliliter, that's the most common. We have 1,000 milliliter ones. We have 500, we have 10, which are really small. It varies up depending on what you're going to measure. If you're, getting a shot, there's no way you're going to use this much. You're only getting small amounts, so that's why they have a syringe with it. This is called a burette when you need exact measurements, like when you're doing a titration. These work really, really, really well. A pipette is one where you suck the units out, and again, the smaller the units, the smaller the marks, the more accurate it is. Okay, so this is going to be more accurate than this. And then here we have volumetric flasks. They just have a mark right here. So if you're making up standard units to use like in the spectrophotometers and things like that, this is the units. So there's all kinds of different ways we measure it, but really what we're doing is looking for the volume by measuring the milliliters. Okay, and temperature, we use Fahrenheit. We always have. When I was in probably elementary school, they were going to switch us to the metric system. It didn't work. It's kind of like telling us we're going to speak French. It just didn't happen. We wouldn't do it. People, in the US, we're kind of independent. We just wouldn't switch. But we're kind of learning things. They're putting milliliters and our regular. Like if you buy a can of pop, it's 12 ounces. But it also says 300 and, well, here, I got one. Oops, got to do it the right way. It also says 355 milliliters on it. So, they're kind of trying to convert us. And some things we buy liters and 2 liters of pop. But temperature is one. The Fahrenheit scale, which we use, is kind of screwy because water boils at 212 and it freezes at 32. If you use the Celsius scale, water boils at 100 and it freezes at 0. That's kind of nice. And then there's the Kelvin scale, which is the absolute. If you look over here on the Kelvin scale, 0 degrees Kelvin, there's no negative numbers in Kelvin. 0 degrees Kelvin is where everything is frozen, so it can only go up from there. It's easy to determine 0 degrees Kelvin. It's negative 273 degrees Celsius. So if you have a Celsius temperature and you subtract 273, you will get Kelvin. Okay. So again, this is the most common one we use, and if we use anything in the lab, that's what we always use is Celsius. Okay. In scientific measurements, again, Celsius and Kelvin is most often used. The only time we'll use Kelvin is when we do gases. Because of their extreme energy, when you're doing calculations with gases, you have to use the Kelvin scale. And again, like I said, it's super, super easy to convert it. And again, the Celsius scale is the one we like to use because 0 and 100, it's very, very uniform. Okay. Again, the Kelvin is because you have absolute 0. That's when everything is frozen. And really it's based on the properties of gases. So we won't really use it right now. We'll use it later. Later on, when we talk about all the properties of gases, we'll always use Kelvin. And again, the thing about Kelvin, since it starts at absolute 0, there's no negative numbers. You don't have negative 1 Kelvin. 0 is as low as you go. Okay, and again, it's very simple. If you want to convert something to Kelvin, take your Celsius temperature. Like if it was 30, then I would add 273 to it to get, and you don't have to worry about the 0.15. Just add 273 to it. And so 303 would be Kelvin. If you have Kelvin and you want to change it to Celsius, you subtract 273. Okay. The Fahrenheit scale is not used for scientific measurements. It's what we're used to. But it's not one that you would ever use in the lab. You always use Celsius. Okay. You can convert Celsius and Fahrenheit if you want. I mean, if it's a big deal. I know a few measurements, like human body temperature is 37 degrees Celsius. When you're in a room, like room temperature, like 70, 72 is around 27. And I kind of use those scales. But again, if you go anywhere else in the world besides the United States, you're going to hear the temperature in Celsius. You're going to see, the speed limit is kilometers per hour. You have, they measure everything in the metric system, or the system international, as they call it. They'll say the SI units, but really what it is the metric system. Okay. Another thing we can talk about is density. Density is a derived unit. Okay. We need to find the mass, which we can do by using a scale, and then with the volume. And it depends on if it's a solid or a liquid, how would you find the volume? It gives us density. Well, what density is how close are the little particles. If it's a solid, the particles are really, really close. If it's a gas, they're far apart away. So it's a physical property, because when I'm trying to find the density of something, it doesn't matter if I'm doing a lot of that stuff, like if I'm measuring the volume or trying to find the density and I'm using a pool filled with water, or if I'm using a glass of water, the density is going to be the same. Okay, so density is a physical property. And again, it's how close are those little particles. Okay, when we take measurements, we use what they call significant figures. And what it does is it makes our calculations more accurate. Okay, and when you're like, what? Okay, if I do a measurement, let's say I'm going to determine a density, and I take the mass and I get like 22.4, and then I take the volume and it's 100. And so I get, when I divide that, I get 2.24. All right, so now I need to report my answer. Well, let's say I do a calculation and I get 2.2497387, okay? Well, what do I report that as? Significant figures are numbers in your measurements. When you take a measurement, if it's 22.4, that has 3 significant figures, okay? If I do 100 and I put a decimal, that has 3 significant figures. So once I do a calculation with it, I have to make sure my answer has 3 significant figures. If I report my answer in 7 significant figures, I'm basically lying. Okay, I'm telling you, I'm making calculations much more accurate than the measurements I took. So whenever you do calculations with your measurements, you need to use your significant figures. Okay, and again, significant figures are numbers in your measurement that you took, and then when you do your calculations, you have to round so that you report your answer in the least amount of significant figures. And we'll talk more about this, but when you're using significant figures, you need to round. Okay, so again, if I have my answer comes out to be 2.24796 and I can only have 2 significant figures, I would round my answer to 2.4. And again, the reason why we do that, you have to pay attention to the significant figures so you don't report an answer that's more accurate than the measurements you took. You're basically lying if you do that. You're saying, my equipment that I took the measurements with is better or more accurate than actual, when I took my measurements. So that's why we use significant figures. I see by the thing we're approaching 14 minutes. So I'm going to quit here. Review a little bit. We'll talk more about significant figures tomorrow. But again, we talked about our different types of changes, physical and chemical changes. We talked about that in the last lecture. But again, a physical change, you can separate it. And I showed, and we talked about filtration, separation, chromatography. Those are all mixtures, okay? And it would be a physical measurement because, again, I'm not changing it in any way, shape, or form, okay? So, and then we have units. We talked about volume. We talked about the metric system. So we're going to have a few discussion questions. Excuse me, geez, I'm tongue-tied today. Discussion questions about that. And then the next part of this chapter will go back with the significant figures, and I'll show you how to do some calculations. So again, if you have any questions, please let me know. This is the end of this part of our going through this part of the lecture.